So in the previous section, we talked about a phase diagram, which looked at the temperature and the heat added. And basically, we walked through increasing the temperature of water from ice all the way up to steam. And we included those phase changes where we added a bunch of energy, but there wasn't a change in temperature. That's called a phase change diagram. What we want to look at next is a phase diagram, which is something a little bit different. So on the phase diagram, we have pressure on this axis, and it might be in atmospheres or torr or even kilopascals. The examples in this book uses kilopascals. And we're going to have temperature on this axis, usually in degrees C or K. In this book, they usually use degrees C. So basically, these are the two axes. And what we're going to look at is the phases of matter, solid, liquid, and gas. So what we end up with is something like this, okay? It's not going to be exactly like this, but this is just an example. So let's look. Well, let's look at this region first, just because I'm going to look at this one first. What about the temperatures? The temperatures are relatively low because we're relatively far to the left on the x-axis in this region. And the pressures are everything except really low pressures. So at moderate and high pressures, we have this phase of matter. Well, at low temperatures and moderate to high pressures, we have a solid. Okay, let's look at this region over here. In this region over here, we have high temperatures, right? We're way over here on the x-axis, and we get down to very, very low pressures when temperatures become lower. So at high temperatures and extremely low pressures, the gas phase is what is existing. And what's intermediate to that is the liquid. So intermediate temperatures and pressures, we get the liquid. You'll notice that there is a temperature and pressure at which all three phases of matter can exist, and this is called the triple point. Okay, so that is basically that. And then up here, which we'll talk about a little bit more in a minute, is called the critical point. Okay, a temperature and pressure above which you end up with a supercritical fluid. And a supercritical fluid has properties like gases and properties like liquids. Okay, so it's kind of in between a liquid and a gas. So this is basically what we have. Now, let's look at what happens if we cross these boundaries. Well, if we go from a solid to a gas in this direction, we would call that sublimation. If we go from a gas to a solid, and we go in this direction, we would call that deposition. And generally speaking, I've seen this curve called the sublimation curve, okay, in this direction. In this case, we have the boundary between the solid and liquid. Well, if we go in this direction, we would call that melting, right, solid to liquid. And if we go in this direction, we would call that freezing, liquid to solid, we would call freezing. That being said, this is often called, for chemistry words, the fusion curve, all right? So the fusion curve between solid and liquid. And then finally, we have the liquid to gas. So in this direction, we would call that boiling, but in chemistry, they'd call that vaporization. And in this direction, we would call that condensing or condensation. And this has been referred to as the vaporization curve. So this is basically what a phase diagram is. Now I'd like to show you what it looks like when it's rendered more artistically or more professionally than just me drawing on a piece of paper. So here is an example of a phase diagram. So if one were to be given a specific temperature and pressure, one could figure out which state of matter that was in. Now, in this case, that's not possible, right, because the axes aren't labeled. But and as you'll see in a few minutes when we see the one for water, where the axes are labeled, we will be able to, determine what phase of matter the water is in at a given temperature and pressure, and that can be very useful. Before we do that, though, I want to talk a little bit about this supercritical fluid idea at temperatures and pressures above this critical point. So this diagram is a little bit hard to see, but it's what it came with, so that's what we're going to use. So here we have a closed container, so we can increase the temperature and increase the pressure, okay? And basically, at the beginning, at intermediate temperatures and pressures, we can clearly see a liquid that's below this line and a gas that's above this line. And these two things are here just to show they're floating on the liquid, and there's a clear distinction. If we heat this up, that increases both the temperature and the pressure. And when that happens, you can reach the critical point, and basically you end up with this supercritical fluid. And the supercritical fluid has properties of both liquids and solids. So, liquids and gases. So like a gas, it can effuse, okay, but like a liquid, it can dissolve. So this gives it some useful properties. And it turns out that there are some substances where you can make a supercritical fluid using fairly standard plumbing type things, okay, and not insanely high pressures. Okay, so for some things you'd have to heat them up to really, really, really high temperatures and pressures to reach supercritical fluids. But for other things, you do not have to do that. And one example of that is supercritical CO2. So if you think about decaffeinated coffee, okay, so we have to get this molecule, this is caffeine, out of the coffee in order to make decaffeinated coffee. And believe it or not, in our labs, we buy this caffeine, they put it in a bottle and they sell it to scientists. They probably sell it to lots of other things. People make Red Bull and whatnot. Okay, so we have this caffeine molecule. Well, how do we get this out of the coffee beans? And it turns out we use a process called extraction using supercritical CO2. And the reason for this is this molecule is relatively nonpolar. It's not completely nonpolar, but it's relatively nonpolar. And carbon dioxide is also nonpolar. So if we take the beans and we extract them with supercritical carbon dioxide, then essentially we can remove this molecule from the caffeine from the coffee beans. If we then take the coffee beans and we put them into atmospheric pressure, the carbon dioxide, we actually use water as well, but the carbon dioxide just flies away because carbon dioxide is gas at room temperature. So there's no downside in this way of using it. If you were to use an organic solvent would absolutely dissolve carbon dioxide, the caffeine molecule. The problem with that is you'd leave some residues from the organic solvent in the coffee beans. You also might extract things that you don't want to extract. So there are reasons that organic solvents are not super useful in this case, but supercritical carbon dioxide is awesome because basically you use it, then you take the coffee beans and you put them at room temperature. They're completely safe because the carbon dioxide flies away. Now, I'm not going into super great detail here, and I'm sure there are some technical things that I'm not aware of, but just to give you a general idea that supercritical fluids can be useful, and supercritical fluids usually exist at relatively high temperatures and pressures for that particular substance, and they behave both like liquids and gases. All right. So the last thing that I would like to do in this section is take a look at a phase diagram here of water. All right. So this was the generic phase diagram that was unlabeled that you saw before, and here's a specific phase diagram for water, which is now labeled. And it's in kilopascals. So 1 atmosphere is 101.3 kilopascals. So this is 1 atmosphere of pressure. And as you can see, between 0 and 100, it's a liquid. At 1 atmosphere below 0, it's a solid. And above 100, it's a gas. All right. If we go down to 0.6 kilopascals, you can see that we would reach the triple point at a temperature of 0.01 degrees Celsius. All right, so just above the typical freezing point of water, we would reach the triple point, but at a very, very low pressure. Remember that the triple point is the point at which the gas, solid, and liquid all occur. So what types of questions might you be asked about this? All right, you might be asked at, I don't know, 50 kilopascals and 100 degrees C, what is the phase of matter? Well, in this one, that's going to be hard to tell because it's not scaled properly. But 50 would be somewhere around here, okay? And I don't remember remember what I said, 25 degrees C, 50 kilopascals and 25 degrees C, all right, would be somewhere around here, and it would probably be a liquid, all right? So they wouldn't ask you for ones that aren't specifically written on the chart, so I guess I should have picked an example that was specifically written on the chart, like at 0.6 kilopascals and 100 degrees C, what is the phase of matter? Well, here, this point is labeled on the chart, and we can clearly see that it is a gas. Okay, so my first example was probably a poorly chosen example. The second thing they can ask you is something that's really strange, and that's the reason I put this one on here, because we can compare and contrast. So for one of these two substances, I don't know what this one is, but for water or this other substance, the solid is less dense than the liquid, okay? And for the other, that is not the case. Now, from your common knowledge of water, you know that the solid is less dense than the liquid, right? Ice cubes float. So the solid water is less dense than liquid water. However, how can you tell that from a phase diagram? Well, the way you could tell that from a phase diagram is to pick any point on this fusion curve, okay? The boundary between the solid and the liquid. So I'm going to pick this random point right here. It doesn't matter which point I pick. Now increase, of course my mouse disappears. Now increase the pressure. So now I'm up here. So I picked a random point and I went straight up. All right, I may not have perfectly gone straight up with the mouse, but the idea was to go straight up, and my mouse keeps disappearing, and that's not helpful. So now I'm up here. Started here, went up to here. What is favored? The liquid is favored. So as pressure increases, straight up is increase in pressure, the liquid is favored, which tells us that the liquid is more dense than the solid. Now let's contrast that to what we have over here. Pick a random point on the fusion curve, the line between the solid and the liquid. Go straight up or increase the pressure. Okay, straight up because the pressure is on the y-axis. Straight up is an increase in the pressure. What did we favor? We favored the solid, meaning we would have to add more temperature to get it to turn into a liquid. There's a bigger boundary here, so the solid is favored. Therefore, in this case, the solid is more dense than the liquid. This is certainly the more typical case, okay? The solid is usually more dense than liquids for most substances, but water is a major famous exception to that, which is probably very good for us because it means like if a lake freezes, okay, the ice rises to the top, which protects the lake from freezing solid. If that didn't happen, it would freeze at the surface and then sink down, and then, you know, depending on where the lake is, a lake could potentially freeze solid. So those are some questions that you could be asked about these phase diagrams, but I hope you can see their general usefulness, right? It's a relatively simple diagram where if you're doing some type of experimental work and you have a temperature and pressure, you can make sure that you're going to have a liquid at that temperature and pressure. Maybe you're doing some low temperature work and you want to make sure your water stays as a liquid. So you want to make sure that at room temperature, how far can I go down on the pressure before it starts to boil or turn into a gas? And I think that's it for this section.